Inequalities on the coordinate plane. Before we get started with how to do this, we need to review a little vocabulary. Because we're talking about inequalities, remember that will mean we're talking about the greater than or equal to, less than, and less than or equal to signs. These will become important as we work on our solution region. Boundary. A boundary is a line that separates one thing from another. If you live in a house, you might have a fence that separates your yard from your neighbor's yard. North High has boundary lines that help to show which students go to East, which students go to North, which students go to Hoover, etc. The solution region, we've been talking about single solutions. Now we're going to have a solution region, which means there will be more solutions available for each problem. You have a friend that goes to Lincoln and wants to know how to get to North for a ball game. You don't know the address, so you begin to give these directions. North is south of Euclid. Here's Euclid. So North is somewhere in here. As you can see, we need to be more specific. North is north of College Avenue. Well, here's College Avenue. So somewhere in here, we'll find North. That's still a lot of place for your friend to drive. We have boundaries. One boundary at Euclid, one boundary at College Avenue. North is west of 2nd Avenue. Well, this narrows it down further. We're getting closer. And finally, we could add one more direction and say that North is east of 6th Avenue. We've narrowed it down, so what we see is that North is less than Euclid, North is greater than College, and I could write the same thing for our East and our West. So now at least your friend would know that North is somewhere in this area that is shaded with green, blue, purple, and red. And that would at least narrow it down so your friend isn't driving across half the city. Where we have North here is what is called our solution region. So North could be anywhere within this shaded area. Let's use what you already know. We have the idea of y being less than negative 3/2 x plus 2. Our first job is to plot the points. You already know how to graph a line. So I know that the positive 2 is my y-intercept, and I'm going to put a dot there. I know that I have a slope of negative 3 over 2, so I'm going to count 1, 2, 3 down and 2 over and make another point and maybe do that one more time. So now we've plotted our points. The second thing we need to do is we need to choose our boundary. Because we have a less than symbol, that means that we're going to use a dotted line to make our boundary. If it's less than or greater than, it will be dotted. And finally, I need to shade my solution region. If I think about standing on the y-axis, so I'm going to stand right here, and y has to be less than. From here, y gets smaller or less than if I go down. So I will shade this part, or this side of the boundary, for for the answer. So this is the solution. So then I want to look for what is a solution. So is 0, 0 a solution? And I would say yes, because I can see that 0, 0 is within the shaded part. Is 3, 2 a solution? Well, if I look, 3, 2 is right here, and I would say no. Finally, is 2, negative 1 a solution? Well, if I go to 2, negative 1, it is right here, but because it's a dotted boundary, any point that's on the boundary is not included if it's a dotted boundary. Let's try one more time. Okay, y is greater than or equal to 2/3 x minus 5. Again, let's plot those points. So starting at negative 5 on your y-axis, a slope of up to and over 3. This time, looking at my symbol, we have the greater than or equal to piece, which now means I can draw a solid boundary. Shading it, again, I imagine standing right here. It says y is greater, and y gets bigger as I go up, so I shade this side. Again, thinking about solutions, what about 5, 1? Well, if I look over here, 5, 1 is in the shaded part, so yes, that's a solution. What about 3, negative 3? Well, if I go to 3, negative 3, I'm right here. Because this is a solid boundary, it is included. Now I'm going to give you a little bit to practice a couple of these. Let's see how to check solutions using equations rather than the graph itself. So I've already graphed this one for you, and I want to know, is 0, negative 3 a solution? Well, if I look at the graph, 0, negative 3 is right here, but it's on a dotted line. But I want to use the inequality to prove it. So I'm just going to take 3 times 0 minus 2 times negative 3, and I want to know if that's greater than 5. I'm sorry, greater than 6. So 3 times 0 would be gone. It says 6 is greater than 6, which is not true. So here, because 6 is equal to 6, so in this case, that worked out right. So not a solution, because as I worked it through and just lost it, 6 is not greater than 6. So 0, negative 3 is not a solution. Another one, is 3, 2 a solution? Again, I want to use the inequality, so I want to know if 2 is greater than or equal to 4/3 times 3 minus 2. So that would give me 2 is greater than or equal to 4 minus 2. Is 2 greater than or equal to 2? Because of the equal part, because of this, we can say that yes, it's a solution, because 2 does equal 2. Let's try 3, 0. So I want to know, is 0 greater than or equal to 4/3 times 3 minus 2? Is 0 greater than or equal to 4 minus 2, 0 greater than or equal to 2, and that would be no. So this is how we would use the inequality to prove solutions. I'm going to let you practice one or two of those. In conclusion, you need to pay attention to your signs. Pay attention to the fact that these two have a dotted boundary. These two have the solid boundary. And then watch for your shading. Remember that if y is going to be greater than, your shading is going to go up. If y is less than, that shading is going to go down.